Hello, in the last class we have discussed some general methods for stability aspects of multi-step methods. Okay. So, for example, Schur criterion we have discussed. So, given a multi-step method, how to find out the stability regions using this Schur criterion. So, let us continue ahead with the stability aspects of multi-step methods. So, let us discuss some further methods. Okay. So, one of the popular method is Routh-Hurwitz criterion. Routh-Hurwitz criterion. So, consider the mapping of the open unit disk of the complex plane to the open left half plane, that is real z less than 0 of the complex z plane. Okay. So, what this mapping does? This maps unit disk mod r less than 1 to the left half plane in z plane. Okay. Then the inverse of the mapping is given by inverse of this mapping okay. So, this is the inverse of the mapping. Okay. So, accordingly okay. So, under the transformation, under this transformation, so the function. So, what is this? This is our stability polynomial. So, this becomes okay. So, this polynomial becomes this. Okay. So, now say this is a star, multiply star by 1 minus z power k. We have, so we are multiplying this by 1 minus z power k, where k is order of the multi-step method. So, we get this, and our aim is to identify this as a polynomial in Z. Okay. So, what was our aim? So, if this is order of the method, so we are multiplying, and this we are expressing as polynomial in Z. Okay. So, then the roots of the stability polynomial lie inside the open unit disk if and only if the roots of the polynomial double star. So, that is of this lie in the open left half plane. So, the roots of the stability polynomial in the original variable R lie inside the open unit disk if and only if the roots of the polynomial double star, this is this, lie in the open left half plane. Okay. So, then the criterion the roots of double star lie in the open left half plane. Okay. If and only if the leading principal minors of the K cross matrix So, this is the roots of double star. So, that double star is of the form okay. So, lie in the open left half plane if and only if the leading principal minors of this matrix okay, are positive and a 0 greater than 0. Okay. So, are positive leading principal minors of this matrix are positive and a naught greater than 0. Okay. And we assume that Aj is 0 if j is greater than this. In particular, for k equals to 2, the condition leads to this, and k equals to 3, and k equals to 4. These represent the necessary and sufficient conditions for ensuring that all roots lie in the left half plane, of course open. Okay. So, these are the necessary and sufficient conditions. Okay. So, to start with, so we have used a transformation. What was the transformation? Z equals to r minus 1 plus 1, and the inverse of this is this. So, under this transformation, the stability polynomial reduces to this, then we have to multiply by this factor. As a result of the multi-step method, linear multi-step method of order k, we are getting this factor. So, then multiplied by that, we get a polynomial in z. Okay. So, then the Routh-Hurwitz criterion states that the roots of this polynomial lie in the open left half plane if and only if the leading principal minors of this matrix are positive and A 0 is greater than 0. And in particular, we have these being the necessary and sufficient conditions for ensuring that all the roots of the polynomial in Z to lie in the open left half plane. Okay. So, let us see how it works out with an example. Okay. So, use the Routh-Hurwitz criterion, okay, to determine the interval of absolute stability of the linear multi-step method okay. So, the given linear multi-step method, we need to determine the interval of absolute stability. Okay. So, we have r equals to, this is a map. Then for this method, we have, so this is given by r square minus 1 and this is given by okay. Accordingly, we have r square minus 1 minus h bar. So, this will be the stability polynomial, which is so this is our stability polynomial. And what is the order of the method? Okay, 2. So, we need to consider this into variable change to this transformation. So, accordingly, okay. So, this should be written in the form okay. So, we can simplify this okay. So, here this get cancelled minus one term there. So, 1 minus z So, this will be 1 minus z square. So, this will be 1 minus z square. So, minus h by 2 z square and this is usual expansion. So, we multiply then sorry, this is minus, this must be minus. So, this will be these terms, then okay. So, this is minus h bar z square plus 4 plus 3 h bar z. This is minus 2 h. So, this is a 0 z square okay. So, now for k equals to this is the necessary and sufficient condition. Accordingly, so using part A, we get h bar to be is the region of absolute stability. Okay. So, this is Routh-Hurwitz criterion. Okay. Right. So far these stability methods, these two general methods, one is a Schur criterion, other is a Routh-Hurwitz criterion. So, they give you using some kind of approach, the Schur criterion via Schur polynomial and then Routh-Hurwitz criterion via kind of transformation. Okay. So, but there are other general methods, in the sense you try to, after all it is a difference equation. So, you try to find the characteristic polynomial and then find the roots. So, that like a general recurrence relation you get the solution. See, once we have a recurrence relation, which is also a finite difference method, right. So, we can get the solution using the roots and hence analyze what happens to these solutions. Okay. So, let us see one such method. Okay. Stability of multi-step methods, parasitic term. Okay. So, we will see what is this parasitic term. Okay. So, let us see with an example. So, consider the multi-step method okay. So, obviously, this is for n greater than or equals to 1, right. So, then so with reference to absolute stability, the reference equation is lambda y. Okay. So, accordingly, this becomes two h bar y n, where h bar is okay. So, the characteristic polynomial r square minus this. Okay. Right. Now, the roots are given by 2 h okay. So, this is given by so these are the roots. So, let us analyze. So, what were the roots? R equals to okay. So, now consider first root, call it R 0. Okay. So, this 1 plus okay. So, this is h bar plus. So, having power series expansion. So, we get 1 there. So, I write that first, then h here, then h square by 2 plus the higher order terms. Okay. So, if you try to approximate, okay, see what was our equation, and naturally the exact solution must be of this form. Okay. So, if we approximate and try to identify with the exact solution, yeah, of course, this is indeed e power lambda h bar. Okay. So, now consider R 1 h bar minus. So, this is h bar minus. Okay. So, this can be approximated as minus 1 minus h bar plus h bar by 2, okay, plus third order terms. So, now this can be approximated as minus e power lambda h bar. I am sorry, this is lambda, which is e power lambda h, and this is e power minus lambda h. Okay. So, one you have this type and other is this type. Okay. However, once we have the roots, the general solution y n is given by C 0 R 0 power n C 1 R power n. Okay. Right. So, where we have R 0 is behaving like e power lambda h and R 1 is behaving like this. Okay. So, now let us take real positive. Then what happens? Lambda real positive. So, we need to compare, because the general solution is this. So, now we need to identify which one is dominating, and really the solution of the difference equation gives stable solutions, right. So, then what happens if lambda is real and positive? R 0 is greater than this. Okay. Then what happens? Then what happens? This grows faster than this. Okay. So, what happens? R 1 power n increases less rapidly than R 0 power n. Okay. Implies C 0 R 0 power n dominates. Okay. This dominates. So, that means the other term. So, out of your solution C 0 e power lambda h n e power minus lambda h n, this is dominating this for this case, which is the exact solution, and this is the parasitic term. However, in this case does not create any trouble. So, why do we call this parasitic term and then why we conclude all this? Of course, this is the exact solution for the given equation, but this is an extra. So, this is also called extraneous part, and this is the parasitic term. But however, in this case it does not create any problem, the overall solution grows as per the exact solution. Okay. So, that means for these values of lambda the solution is stable. Okay. So, let us consider now the other case. Okay. Lambda is negative, then for of course, h is positive. Okay. So, then C 1 r power n will dominate C 0 r power n as n goes to infinity for a fixed h. Okay. So, therefore, the parasitic term, okay, fixed h. So, this parasitic term increases. Okay. So, this creates a problem. Okay. So, that is how. So, for lambda real and positive it agrees with the true solution, whereas for lambda negative this parasitic term creates a problem. Okay. So, this is another kind of stability analysis. Okay. So, let us see this a little more from a little theoretical point of view. Relative and weak stability. Okay. So, relative and weak stability, with respect to what it is relative, we will see. So, consider this. Okay. Say, so general solution is given by, so for a general method, okay, j is 0 to L, C j R j lambda h, okay, right. The parasitic terms power n goes to 0. Yeah, this is true, because as h goes to 0, the parasitic terms goes to 0. However, for finite h, for any x n, one would expect it to be small compared to see. So, that means we are bringing out the concept of relative stability. So, relative with respect to what? Relative with respect to the principle, in the sense the exact, okay, R 0. Okay. So, this implies for sufficiently small h. So, this is relative, okay. It is a comparison, the parasitic terms with the exact. So, extraneous terms with the exact, okay, right. So, a method is relatively stable if the characteristic roots satisfy for all sufficiently small. So, that means let there be some parasitic terms, but compared to the exact, these extraneous must be small for sufficiently small lambda h, okay, the impact. Satisfies the strong root condition if these roots which would contribute to the extraneous terms, if the magnitude at, of course, for h 0, if the magnitude is less than 1, then we say it is a strong root condition, okay, right. So, remark relative stability does not imply the strong root condition, and if a linear multi-step method is stable, but not relatively stable, it is weakly stable, okay. So, relative stability does not imply strong root condition, and if a method is stable, but not relatively stable, then we say it is weakly stable, okay. So, for example, the case y n plus 1 plus 2 h f n. So, for in this case we have seen, okay. So, this does not hold. So, hence this method is weakly stable, okay. So, that is how we can categorize the relative stability and weakly stability, okay. So, we have some criterions to systematically capture the interval of stability, region of stability, but there is another concept to analyze parasitic terms and then say how the methods behave. Okay. So, let us analyze with some more examples. Okay. So, for example, consider okay. Right. So, this implies on y dash we get okay. So, we have so this will be the characteristic polynomial, then the roots so if R is this, we get these roots. Okay. Accordingly, Z1, so Z1 which is so this can be written as this can be written as so this is for what? If h goes to 0, r goes to 0, r square goes to 0. So, with that we can linearize and try to get this. So, you can identify. So, we have done it in the last example. Okay. So, 1 plus lambda h e power lambda h okay. So, as h goes to 0, Z1 behaves like and Z2 behaves like. Okay. So, therefore, y n C1 z1 power n plus c2 over n. So, this is c1 so this agrees with exact solution, and this is parasitic term. Okay. So, now if lambda is negative, this grows and creates trouble. Okay. So, this is another example where we could analyze. Okay. So, now for these multi-step methods, there is a small technique. Given your characteristic first and second characteristic polynomials are rho of zeta and then sigma of zeta. So, for a particular method, if rho is given, can we determine the corresponding sigma? So, this is another small trick involved. So, let us try to do that. Okay. So, given given this, how do we determine? Okay. So, one may also refer the numerical solutions book by Jain. Okay. So, to know lot of examples. Okay. So, consider so this is our general linear multi-step method, k-step method. Then the error. Okay. So, this is the error. Okay. Then recall this linear multi-step method said to be of order p if equal to 0, okay. So, this gives a pth order method. Okay. So, accordingly T I plus 1 reduces to okay, right. So, this is identically 0 when y x is a polynomial of degree less than or equals to p. Okay. Right. Now, observe that the constants C I and P are independent of y of x. So, let us choose y of x equals to this, then double star. What was our double star? This. So, this goes like okay. So, this is e power k h minus a upon so this can be written as rho of E h minus h okay. So, it is right. So, T I plus 1 this must be behaving like this, okay, right. So, this implies we can some new constant, because there are some terms left out after getting cancelled x I. So, that I have put it to this constant. Okay. So, this is the relation using which when rho is given, how to determine sigma. Okay. So, this will suggest us. Okay. So, let us work out some problems how to determine exactly for a given example using this relation in the coming lectures. Okay. Until then, thank you. Bye.